Citilabs builds software to model and simulate your city. Cube is a modeling platform that allows users to ask what-if type questions regarding changes to the transportation networks, land use, and the population. Cube Voyager allows you to build regional models to understand large-scale travel demands. Cube Avenue is a city simulation to model the dynamics of congestion throughout a day. Cube Dynasim is a traffic simulation to model all aspects of traffic and parking. All of the Cube modules work together to help users understand the immediate impacts of decisions that are being made and the effects of those decisions in the future.
Consider a new proposed development. If it's built, what will happen to the traffic in the area? How can you better understand the congestion in the area and what impacts the development will have? Will extending a rail system to the new development help with congestion levels in the tunnel that is leading there? Maybe if we increase the toll for the tunnel, how much more revenue will be generated? And for that matter, how would the increased toll affect the ridership on the new rail line? In ArcGIS, we can show the input data that goes into a modeling process like this. Fundamentally, two types of data are required: a routable transportation network and information that describes the land uses and population in the area. In the case of a model of Singapore, we've divided the area up into 40 different neighborhoods. When we click on one of these neighborhoods, we can see information on the population and the amount of employment in the area. Likewise, for each section in the transportation network, we have information on the type of roadway, the capacity given by number of lanes, the length of the roadway, as well as the speed people are allowed to travel. Finally, there are data that describe how people in the area travel, with information on how many trips people make per day, and how far people will travel to go to work or to go shopping. These inputs go into a modeling process which takes the input data on land use and transportation networks. The information on the population and the employment is used to determine, for each neighborhood, how many trips are generated by people living there, and how many trips from other neighborhoods are being attracted to the area for work, play, shopping, or dining. Then the model starts connecting the population generating the trips with the areas that are attracting their activities. These connections, this distribution of trips throughout the city, provides a complete picture on where people travel to and from. Then, the question is, as people move around the city, what mode of travel will they choose? Will they drive, take a taxi, or go by public transport? If they choose public transport, are they going to walk to the train, or will they get on a bus? Once they select a mode of travel, the last question is, how will they choose their route? As the models run, these individual decisions are being simulated. It works in a very iterative fashion as the simulated population learns the best decisions for their own situation. The first time everyone may choose to take their own vehicle, but then the model feeds back that the congestion is way too high and it would be much quicker to take the train. The model iteratively loops over these decisions again and again until everyone is finding their own best possible way to reach their destination. This or any other modeling framework can easily be implemented in Citilabs' Cube Voyager software. The modeling platform lays out in a very similar flowchart type of interface these fundamental questions and how they're being modeled. Users can easily see the input data on the left-hand side and the output coming out of each step on the right-hand side. It provides a very flexible environment for modeling the travel in any city. Directly from the flowchart, we can open up the output data in Cube and immediately see the traffic volumes and congestion levels throughout the city. We can zoom in and identify specific corridors that are the most troublesome. Now, if we turn off the congestion map and add a path file to this network, we can select any individual roadway and easily see, for just the people using this roadway, where are they coming from and going to. Can we alleviate some of the congestion by offering a more direct public transport option, connecting these origins and destinations? Likewise, if we open up the matrix of trips that are being loaded onto the network, we can click on any individual neighborhood to see where people are coming from to go to this neighborhood and where they go when they leave this neighborhood. Let's open back up the input network. This time, instead of in ArcGIS, we'll just double click it in the flowchart and open it up directly inside of Cube. We can zoom into an individual intersection. Here, if we open the same intersection in Google Maps, we can see the street view and the number of lanes and movements through the intersection. All these details about an individual intersection can be coded up to enhance the network representation directly inside of Cube and provide more operational details to model. Models can be developed at any level of detail. We can develop very simple models using very basic data, and as we add more information around intersections, for example, or enhance the public transport information with schedules and more details around the transfer connections between lines, we can use the model to understand the benefits of operational level improvements in our city. Likewise, we may look at the employment data, not only by total employment, but by type of employment, commercial, retail, service workers. We could look at the population data by their households instead of simple population numbers. And the households themselves can be disaggregated into the number of households with access to specific numbers of vehicles, or by income level. If we want to model longer-term questions on how land uses may change given enhancements to the transportation system, we can use Cube Land and add land use data itself into the modeling process, with information on square footage of commercial, retail, and residential space, as well as information on pricing. We can also model the movement of freight using Cube Cargo, just as we're modeling the personal travel using Cube Voyager. We can gather information on the commodities that are being imported to and then consumed through manufacturing process or the retail sales of goods, and model these commodity flows throughout the city or a larger regional area. Here we have also built a demonstration of a freight model in Singapore using Cube Cargo. Similar to the transportation network, freight movements have their own transportation components. We have ports and airports bringing goods into an area. And we have the rail and truck movements that carry the goods throughout the city. In addition, there are distribution centers, warehousing centers that all need to be taken into consideration. When we open up the outputs from the freight model, we can see the truck volumes in black, along with the passenger cars we were looking at earlier. We can identify areas where trucks are significantly adding congestion levels and test network changes that provide better facilities for freight movements. Or we can see the impacts of policy decisions to keep trucks out of an area during the peak travel periods. Cube Cargo can consider all types of commodity movements and model in detail the delivery vehicles bringing goods to their final destinations. You can consider this by different commodity types, modeling all the decisions of how we're moving fresh fruits and vegetables versus auto parts, electronics, or raw materials for manufacturing. If we go back to our model in Cube, these models once developed can have an unlimited number of scenarios examined by altering the transportation networks or land use and population data to create alternatives. There's so much value to being able to run and test alternatives. The model is a resource for many agencies and consultants in a region. It will be used by the highway, street, rail, and bus agencies, as well as the economic development and land use planning departments. Given the shared nature of this resource, the model can be distributed and run directly in Cube, or for more security and control, the model can be published out to Cube Cloud. In this way, not all of the users need to be experts in Cube. Instead, users can create and edit input data using ArcGIS and run models directly through a simplified user interface on the web. Once a model's been published, we open Cube Cloud in a web browser and log in. We select our Singapore model and we can see the input data going into any particular scenario. Here, fundamentally, the roadway network and land use data, as described before, become the key inputs. We'll consider a new development in the Jerome Lake District. We can easily create a new scenario, and in this case we can edit the land use data in ArcGIS. Then, we simply browse to the data and upload it to Cube Cloud. We click on Schedule Scenario, and our model will run on the web just as it would in the software on our desktop. Now, once the model is completed running, we could certainly download and open up these files in ArcGIS or Cube just as we've been demonstrating. But regardless of if the models are run in Cube or in the cloud, the results can also be published directly to ArcGIS Online. For our scenarios here, with the new development in the Jerome Lake District, we can log into ArcGIS Online, and now we see a before and after comparison, looking at two different scenario outputs, overlaid in a story map. Cube's integration with ArcGIS Online makes it easy to share your analysis with coworkers and even the public. If you are a technical modeler who's developing and enhancing your model, a transportation engineer testing operational improvements to implement today, a planner developing scenarios to meet your community's vision for the future, or a director presenting results to the public and elected officials, Citilabs provides the most flexible and open transportation and land use modeling platform for planners and transportation engineers around the globe. With decades of model development experience and a close partnership with Esri, Citilabs strives to use new technologies to expand access to urban models and improve communications with the local communities. Citilabs solutions enable governments to make the most informed transportation and land use development decisions to create a better future.